All right, I had a lot of fun doing the stepper motor video that I did, and it made me think that maybe I should spend some more time talking about these programmable logic devices. They're actually kind of clever, and they don't make them anymore. I think you can still get them, but they're very, not very popular. But they were so cool, and I think a lot of people who are really into retro computing and stuff would really enjoy these things and kind of know how they work and be able to use them in their projects and stuff. They're really good for putting together a bunch of glue logic that's sometimes required for old designs. A lot of times things didn't really quite fit together. You had to do a lot of glue logic to get things to go. And so let me just first show something. I have a little FourBit counter here. And it's just a simple little counter. I've got a 555 over here that's supplying the clock. So let's talk about what these things are, what they can do, and kind of how they work. Let's talk about that first. So yeah, so what are these things? So there's different kinds. There's things called PALs, Programmable Array Logic, and then there's things called GALs, which are Generic Array Logic. Okay, and this particular device that I'm using was made by the company Lattice Semiconductor, and it has a particular number. These are quite popular, 22V10, and the way that what that stands for is there's actually it's a 24-pin device, and it has the ability to have 22 inputs and 10 outputs. So out of those pins, 22 can be configured to be inputs, 10 can be configured to be outputs, okay? So, and this is all TTL level stuff. So maybe this is CMOS. Yeah, this is all CMOS level stuff. There's this picture here that's not very good to tell you what's going on. Let's try to find a better picture. All right, the first thing we're going to talk about is, let's see, I think the first thing we'll talk about is the input, okay? And so these things are programmable, and they're not one-time programmable, they're electrically erasable, so you can use them as many times as you want. And this is what's inside the device. And you can see that there's just a whole bunch of lines, okay? And so you can imagine these are inputs, okay? And these are things that you want to connect together. So these are kind of like stationary wires. And let's say you have an input here, and you want to route that to an output. Well, you would connect it to one of these wires, and then it would go down and then go over to the output. So it's kind of a road map, right? It's a bunch of streets, and you can go in and out of the streets. Now, each one of the inputs, so these are all inputs, 1, 2, 3. So pins 1 through 11 here are all inputs, and pin 13 is an input. That will always kind of catch you. Pin 13 is an input, then all the rest are outputs on this device. And so for each input, pen here. So for each input, we'll look at pin 2, okay? So pin 2 comes in, and pin 2, I'm going to draw it bigger here. Pin 2 comes in, and then it goes out. And it goes out like this, okay? They draw it like that. And what that says is you have some pin 2 coming in, and then we're gonna send its high-low state out here on this wire, and we're going to send the inversion. We're going to send the not signal on this one. So every time something comes into this matrix is the original signal and the inversion of that original signal. So you always get, if A comes in, you get A and you get not A. You get B and you get not B. So you always get both of those. So when you get to program this matrix, you can choose either the original signal or the complement of the original signal, okay? So that's how that works. And so each one of these is that way, all right? And so you can connect these things to different things, and you can go up and down and side to side. And so let's see, what's the best way to describe this? Let's say that you have two things. You have pin 2 and you have pin 3, okay? And those are going to come in, okay? And so they come in on these two things. Let's say you want to take the AND of these two. You want to have the AND come out the other side. So these are input pins and these are output pins. How do you get an AND function to get to the other side, okay? Well, you bring these and you run them into one of these output pins. Now these output pins have these little boxes around them. And these boxes are a bunch of circuitry inside each one of those boxes. So each output pin has some really complicated circuitry. So let's see if we can find a good picture of that. There's some good ones and there's some bad ones. Let's see if I can find the good picture. This one. This is a good picture. Okay. All right, so this is one output pin. So of those 10 outputs, these are duplicated 10 times, okay? So you have a bunch to choose from when you output things, right? The matrix that I showed, those lines can route things and they can also perform AND functions, okay? So you can do ANDs in that matrix. Now, it comes into a big OR gate, okay? This is a big wide OR gate, right? And it can do ORs. So you can do ANDs over here in the matrix. Okay, the matrix is over here. You can do ANDs in the matrix and you can do ORs here. So ANDs and ORs, okay? And then we can bring those in, okay, into this thing. And we can send it through different ways, okay? So this is a bit complicated. So the output pins can also be input pins. Remember, there's 22 input pins and 10 output pins. So the output pins can either be an input or an output, okay? And that's what this line does right here. This line says enable the output or disable the output, okay? So this is kind of an enable line here, okay? So we're going to enable the output if we're going to have this as an output. Now, if we're going to use it as an input, we're going to come down this way, and I'll explain that later, but that's how the input gets in. But the output has to make it through here, and so we need to enable this. All right. Now, there's a flip-flop here. It's actually a D-type latch. It's a D-type latch. And then there's something called here a 4-to-1 multiplexer, and that's kind of a fancy word for just it's a switch. There's 1, 2, 3, 4 things you can switch. So the output here is one of 4 things. You get to choose. So in this particular case, what we want is we just want this OR function. We want to come in here, and we want to come up here, and we'll just come out to this one, and we're just going to wire these two together, okay? You can wire these two together, you can wire these together, you can wire these together, right? You can choose which one of these you want to have go out. So you can have just logic go out. So we can perform the AND function out here in the matrix, and then just bring that straight through. Or we can do an OR function. We can use this. We can bring in A and B into here and do an OR function and bring it through. And we can do all sorts of things, like exclusive ORs. We can do all kinds of things. All right. So that explains how you get things out, okay? And in fact, you can either take the regular out or you can take the inversion. So there's an inversion here too. You can either take the regular signal or the inverse of the signal, so you can do that. It gets inverted a second time here, but you can either take either one. All right, so what else can you do? Well, there's a D-type latch here, and you can either take the Q output or you can take the negative Q output, okay? And we'll show an example of that later. But so you can bring in the signal as is, you can bring in the signal and invert it, or you can take it through the D latch and you can bring out Q, or you can go through the D latch and you can bring out not Q, okay? That's how all the output stuff works. Let's talk about the input stuff. In the input stuff, you would disable this, and now the input comes this way. And now over here, you also have a choice of 2 different things. You can either bring these things, you can wire these things together, so the input goes right out. And it has one of those things, again, where you send both the signal and the inversion of the signal, the complement of the signal, bring those both across. Or you could actually hook it up this way, and you can bring the not Q signal over and send that into the matrix. So you can do all kinds of things. So that's each one of those 10 pins has this circuitry in it, okay? So we've seen that we can just do a simple gate, you know, ANDs and ORs and things like that. But what about this D flip-flop, okay? So remember, D flip-flops are, let me write over here. I can just write on this. Here's a D flip-flop, okay? So here's a D flip-flop. So a D latch. This is a D latch. If you want to turn a latch into a flip-flop, okay, the little thing here means that it's a clock driven, and it's on the rising edge of the clock. And there's a D input, and there's a Q output, and there's a not Q output, okay? And in order to make it into a D latch into a D flip-flop, you wire the D input to the not Q. So think about this. If you reset the flip-flop, then this is a 0, and this is a 1. And so a 0 comes out. And if you send a positive signal, remember this was a 1, and that's on the gate, that's on the D input. So if you clock it, it's going to send the 1 through. Now this will go to a 1 state. And this will be a 0 state. And the next time you get a rising edge, the D will be 0. So you'll get a 0 output. So it toggles back and forth 0 and 1 and 0 and 1, 0, 1. So that's how you use a D latch and use it as a flip-flop. So can we do that? Can we turn this into a D flip-flop? Well, here's our D, and we have to get it from somewhere, and here's our not Q, so we have to get it over here to D somewhere. So somehow we're going to have to get our not Q and plug it into D. And the way we're going to do that is we're going to bring our not Q here, we're going to make this wire happen, okay? And then we're going to make this wire happen, and it's going to go into the matrix, okay? And we're going to make this connection here, and we're going to make this connection here. And that not Q will come over here, and it'll come up into here, and it'll go into D. And then every time this thing clocks, it will keep inverting. So you can see this thing's very flexible. We can do it all sorts of different ways. Now you don't have to worry about how do you do this. The compiler takes care of that when you write the program. It automatically figures out how to wire everything up, so you don't need to worry about that. But we need to worry about how it works. So this is how it works. All right. Okay, so let's say we want to build a counter, and normally you would build a counter like this. D, not Q. And then the Q comes out, and then that would go into a flip-flop. And there's a 2-bit counter, okay? This one clocks, this one goes half the speed, and this one goes half of that speed. So that's how you would build a 2-bit counter, okay? Now, unfortunately, you cannot build this because all of the clocks are wired together. They're all synchronous. So you can have 2 flip-flops, okay? You can have a flip-flop here, and you can have a flip-flop here, but the clocks are synchronized, all right? And so you can't do this. You have to figure out some way else to do it, okay? And there's ways of doing that. There's, if you put some logic around this, you can get synchronous counters to work. And so if you bring Q out and you bring this Q out, then you have A and B, and it'll count in binary. But you need to do some things to make this work. All right, I found some nicer drawings here. You don't have to put up my squiggles. So this is actually how you would build a regular one, right? You actually would run the not Q into the next clock. And so the not Qs are always connected to the Ds. Okay, so they make these latches into flip-flops, and the not Qs always feed into the next one. So you get, this is a 4-bit counter, right? So if you could do that, that would be great, but you can't do that because they're all synchronous, okay? So this is a trick that makes it work synchronously, okay? You can see that all the clocks are tied together. So the clocks are all happening at the same time. Now the first one is connected the way that we always think. The not Q is connected to the D. So that one works just fine. But the output of this one, now, instead of going directly to D, it gets ANDed with its not Q output. So normally, this one would also have not Q in there, and this one would have its not Q in there. But because it's synchronous, it's not cascading, and we need to do some tricks. So we need to put in this AND gate here for this one, and then we need to put in a 3-input AND gate in order to make this one work. And if we had another one, we'd have to have a 4-input AND gate, then a 5-input AND gate, and that's the way that you would build a counter. And so this is the way that you need to actually wire up the GAL to do counting. And luckily we have lots of gates around, because that's what that thing does. That's what it does really, really well. It has lots of ANDs and it has lots of ORs. And so it's easy to build this circuit, all right? All right, so you remember the little 4-bit counter that we had over here? Well, it's programmed to do this. It actually has its circuitry wired up to be like this, and then it's able to count, okay? And I'll show you how to do that later when we get into actually programming these things. But you do have to do some funny things to make these things count correctly, and that's why you'll see the code look strange when you're counting it. You have to put in these extra AND gates to make it all work. There's another type of counter though that you can wire up very easily. Let me show you that one. Okay. And it looks like this. All right. And again, it's all synchronous clocks. All the clocks are wired together. But here, we just take Q and put it into D, and Q put it into D, and then not Q and put it into D. And this ends up being a strange device. This is called a ring counter or a Johnson counter. Okay, it has 2 names. Johnson counter. All right. Now, this one's a bit strange. Okay, so when you clear this thing, you're going to have 0, 1, 0, 1, 0, 1, okay? And then you're going to clock it, okay? So what is the D input at the very beginning? It's 1. It's this down here, it's 1. So then this one will go high, okay? So the next state then, this one will be 1, 0. That one will change, okay? But none of the others will change because this was a 0. So when you clicked it, this one will just bring in the 0, and this one will bring in the 0. Okay, so these won't change. 0, 1, 0, 1. Okay. Then if you clock it again, this is still a 1. Okay, so 1 will come through here, but now this was a 1, and this will get clocked, and this will become a 1. So now we'll have 1, 0, 1, 0. So now this one goes high, and it cascades around. So instead of actually kind of doing the thought process here, let me show you what it actually ends up looking like. All right. So the Johnson counter is this one. This is a 7-bit Johnson counter. Okay. And so when we start out, we're going to get 1, and then it's going to keep going. It's going to replicate itself until it gets to the end. And then once it gets to the end, that last flip-flop finally changes state. And this ends up being a 0, which feeds back around. So then this thing starts replicating zeros. So first it's replicating 1s, and then it starts replicating 0s. And then it starts replicating 1s again. Okay, so that's what it's doing here. It's replicating 0s right now. And once that changes state, now it's starting to replicate 1s. So this is a Johnson counter. And you can see that even though it's 7 bits, it's not giving us 2 to the 7th counts. It's only giving us a smaller number of counts, 16. It's giving us 14 counts, I think. And so, yeah, so Johnson counters are interesting, but probably not very useful in most things. They might be in some things, but anyway, this is what a Johnson counter does, right? All right. Okay, so we've seen a 4-bit counter, we've seen a Johnson counter. We have seen we haven't seen, but this is an 8-bit counter. Okay, this is an 8-bit counter. And so it'll take a long time for it to go, because it has to go all the way to 2 to the 8th, right? So that's an 8-bit counter. And I'm going to show programming examples of all these things. So Johnson counter, 4-bit counter, 8-bit counter. Here's an 8-bit counter with something special on it, okay? So this 8-bit counter, let's see, I need a piece of wire. All right, so this one is special. It's an 8-bit counter, but I programmed pin 2 to do something special, okay? Pin 2, if I ground pin 2, everything goes to 0. And then if I put pin 2 at 5 volts, it starts counting again. So it's a reset pin, okay? I've added a reset pin. All right, so how is this reset accomplished, okay? How do you do that? So let's take a look at the diagram here again. Here's our flip-flops. The wired is a flip-flop. It's a D-latch. This wire is a flip-flop. But here is an SP, and here is an AR. So what does that mean? AR means reset, and SP means set. So this is the set, and this is the reset. And what I'm doing is I'm programming pin 2. Okay, so pin 1, clock's going to come over here to pin 1 always. Okay, pin 1 is always the clock. And pin 2, I've programmed to come in, and actually one of these lines is the AR line, okay? So I'm going to connect it somehow to AR, okay? So this goes to here, and this goes to here. I'm going to connect AR up. So, and I did that for every single flip-flop. So when I ground pin 2, it pulls the reset line on every single flip-flop, okay? So that's what happens here. And again, we'll show you code on how this works. Okay, so. And if you want everything to go into high state, you could have everything wired up to the set pin, and then you can set everybody instead of resetting everybody. All right, so set reset. So that function is in there as well. Okay, so I showed you 4-bit, I've showed you 8-bit, I showed you the Johnson counter. Now let's just show you some generic logic, okay? So this one is just generic logic. All right, so this one is going to be a little bit difficult to see. You might need to slow this down on YouTube, okay? But the first two LEDs are the counters. So 1, 2, 3, 0, 1, 2, 3, 0, 1, 2, 3, 0. Okay, the next LED is OR. So if one of the lines is high, then the output will be high. So either 1, 2, or 3. So 0, nothing is 0 is low, but 1, 2, and 3 all end up being high on this one, okay? The next one is going to be AND. So it's going to be low, low, and then when it equals 3, 0, 1, and 2, it has to be 3 for it to be high. So watch this LED here. It'll be 0, 1, 3, right? 1, 2, 3. Go 1, 2, 3. Okay, and then the last LED is exclusive OR. So the 1 state and the 2 state will give you a high, but the 3 state will give you a low because it's OR but not both. So if they're both 0 or they're both 1, you're going to get a low on the output. So that's the way that third LED works. So I included this one just as a really, really simple example of how you do simple logic and how you program that. Okay, so we have a bunch of things now. We have our counters, we have our Johnson counter, we have logic. We sort of understand these devices, although they're very confusing when you first look at them, and it'll take you a while to figure out how these things work. Some of the strange things, like I said, is pin 1 is reserved. Pin 1 only does clock. You can't use it for anything else. It's just clock. Let's see what else. Well, if you're not using the latches, you can use it as an input, but it's the only one you can use for clock. You can't route clock from anywhere else. It has to come from pin 1. Okay, so pin 1 always is the clock. And this example here just shows you that you can have certain states in this thing. You can have it set so that it ignores the flip-flops and it just acts as logic. And the output can either be a high true or a low true. That's what these two states are: active high, active low, active high, active low. I don't know why they had to include that, but they did. All right. So there you go. So maybe maybe the front picture makes a little bit more sense now that you've kind of seen it. Here's the clock, and the clock comes over the top here and goes into all of the D latches. This big section in the middle here is the programmable AND array. So AND, it's 132 by 44. So it's a big array, 132 by 44. And so AND functions can happen here. And then OR functions happen at the individual outputs. Remember, these are all the OR gates. Now they're not all the same though. See, this one only has 8 ORs, and this one has 12 ORs. This one has 14 ORs. This one has 16 ORs, 16 ORs, 14 ORs, 12, 10, and 8. So they're not all the same amount of lines that go into the OR gates. So if you're actually building hardware that requires you to have lots of ORs in the logic, then you may be restricted on which pins you can use. You know, if you really needed 16, OR functions, then you have to use either one of these 2 pins. They're the only ones that have 16 lines. But anyway, you'll get an error if it's not wired up right, I think. It'll tell you that it's not available or whatever. Okay, this is WinCUPL, AppMail version. You can get this online for free. And this is the example of the first one I showed, which was the 4-bit counter. So this is very, very simplistic. So let's go through it here. We have a section at the top here that you need to always fill out. You give it a name, and it fills in the part number. I think, I don't remember. I never touched that one. I do change the date. This is an old file. I put in my name, and it's very important. The most important thing here is you need to put in the device. So this is a G20V10. So you need to make sure you have that in there so it can compile correctly. Then you can define the input pins, which I have here as pin 1 is clock. And that's really the only thing that is the input. And then there's going to be 4 outputs. And you can individually specify them, or you can use the pin node command, which outputs these to a series. So if you have a Q0, 1, 2, 3, you can then type it in this format here, and this one here. And you can say that pins Q3 through 0 are equal to pin number 17 through 14, and then it automatically does the rest for you. Now remember that a 4-bit counter, a synchronous 4-bit counter, was a bit odd. We had to have all those strange AND gates in there, and you can also do it this way. So the very first one is as simple as can be. You take the not Q and route it to the D input. So that's what this does. This says on the Q0 D latch, the D input, so the dot D says this is the D input. Spaces aren't required in this language. I think you can cram everything together, but for readability, I did it this way. So the D input of the latch is going to be wired to not Q0. So that's that simple thing. And then the other one's a little bit stranger. You've got Q1's D is going to be tied to Q1 exclusive ORed with Q0. And then Q2 is hooked up to Q2D is hooked up to Q2 exclusive ORed with Q1 and Q0. And anyway, so that's the way you do that one. All right, and we've seen that. So let's take a look at an 8-bit counter. Here's the 8-bit counter, and you can see the file is exactly the same. I've just expanded on how many lines we have here. So now we have Q0 through 7, and I've changed the pin nodes here, so they go from pins 14 to 21. And you see you have to add a whole bunch more and functions to make it work. So that's the simple 8-bit counter. And then let's take a look at the Johnson counter. Let's see, the 7-bit Johnson counter looks like this. So the first D latch is connected to the last not Q, and then everything else just is connected to the Qs. So I think if you take a look at the schematic that I showed and you take a look at this, I think it'll all make sense. So that's how you define a Johnson counter. And then the last one we looked at, oh, not the last one. Let's see, we have one more. We have the 8-bit counter with a reset. So it's exactly the same as the other file. We have all of our 8-bit stuff in here. And then we're going to add some commands here that wire up the AR, which is the reset line. So the AR line on each of the 8 D-latches is going to be connected to not reset. So when I grounded reset, it did the reset. Okay, so that's how you would do that. And I also had to add at the top here, pin 2 equals reset. Right. So you give pin 2 a name, reset, and then pin 2 is now not pin 2. It's now connected to all of the reset pins. So that's how that one worked. And then the very last one that I showed was this one, which showed all of those little logic gates. So we have a 2-bit counter. So 2-bit counters are very easy. And then I had 3 types of gates. I had an OR gate, an AND gate, and an XOR gate. And so you can just see here that what symbols are used for OR, what symbol is used for AND. So you use a hash sign for OR, an ampersand for AND, and a $ for XOR. So kind of strange, but that's the way they do it. All right, so there you go. Those are all the sample files in CUPL. You make all your corrections here. It's just a text editor. And then you want to compile it. You go up here at the top, and you go over to this box right here. It says Device Dependent Compile. And if you click that, it'll come up and say, do you really want to do this? You say yes. And then you get, I don't know if the pop-up window is showing in the video here or not, but you get a pop-up window that says if you were successful, or if you had any warnings and everything, you just say okay. And then down here at the bottom, I know you can see this. Down here at the bottom, it says you had some, you did have some warnings, but they're not errors. It just says, hey, some things didn't get connected up. You didn't connect the reset line. You didn't connect the preset line. And that's okay. You don't need it to come up. It just gives you a warning. Hey, maybe you wanted to, maybe you didn't want to, but we're just, they're not going to be hooked up right now. So it'll operate fine without connecting those. All right. So once you have compiled this thing, you notice over here in the upper right, you now have a couple files. You have the an ABS file, a JED file, and a PDF file. I believe it's the JED file that's used in the programmer. Okay, so let's bring up another window. I'll show you how to program these things. All right, this is the MiniPro Programmer, and you need to select an IC, which is here. You can go to the search device, and you can put in a, let's say you have a 16 V8 part, and it'll come up and it'll show you that you have an Atmel part or a lattice part, and a bunch of lattice parts for a 16 V8, but we're using a 22 V10, so we're going to put in a 22 V10 here. And I have this checked here for gals, PDL gals, and so gals. Read the number on your IC, and mine are D types. And so make sure you either have an A type, B type, C type, D type. Mine is a D type, and make sure you type in the right one, because it won't program correctly if you don't. So I have D here. So I have a GAL 22 V10D. Now I found that the MiniPro doesn't work with other manufacturers. That really the only parts I've been having success with are lattice parts. So I buy lattice parts and I use the programmer with lattice parts. I tried programming some other parts, it didn't work, but the lattice parts did work. So there's a tip. So once you get that in there, then you need to actually open up the file that you're going to program. And these all default to the JED files. Okay, so we're going to have a JED file. So let's say we're going to program the Johnson counter. Okay, so we have a 4-bit Johnson. So we'll click on that, and it's automatically loaded. Okay, and then all you need to do is then push the program button. Let's see here. Let me go ahead and put a part in, and we'll program it. No harm, no foul. So I've put a part in the programmer, and now I hit the P, and it comes up, and you don't need to change anything. You just hit the program, and it erases the chip, and then it programs it, verifies it. There you go, and done. It's really quick. It's really fast. Works great. There you go. That's all there is to it. That's about all I know, and I hope it helped.